Let's summarize the key points we emphasized in the first part of this presentation. First, we talked about the transistor. This component is the basis of all the electronics of our time, with which we make the bits to store data, and the logical circuits, such as the AND or NOT gates, with which we create the logic of programs. With bits we represent numbers, that we then use to do any kind of mathematical calculation. We have seen how with bits, with the on-off values, we do a sum, with the carryover of 1 just as we do with decimal numbers. We have also seen how to associate numbers with other meanings such as the letters of the alphabet, or anything else. We have seen that it is the programmer who decides what meaning to give to the bits based on criteria that he himself establishes. And we have seen that a sequence of bits in itself does not mean anything, because it is the programmer who gives it the meaning he needs for the processing he wants to do in his program. With logic circuits, and or not, and all the various possible combinations, we make comparisons to determine whether two sequences of bits are the same or different. And if different, which is higher and which is smaller, which comes first and which comes next. We've also seen how to build an electronic calculator with all these components. Then we met the brilliant mind of Alan Turing, the father of computer science and artificial intelligence. And through his intuition of a machine based on a tape that goes up and down, which contains elementary instructions to be carried out step by step, it is possible to develop any kind of processing. We have also seen that over the course of a few decades, the industry has managed to miniaturize these electronic circuits, compressing millions and trillions of bits into few centimeters. A similar compression capacity exists also for the logical and or not circuits with which the CPU is built, the heart of the Turing machine that executes elementary instructions. With the information about the transistor, bits and logic circuits, we were able to describe and understand the logical scheme of an electronic calculator. It is an all-hardware electronic machine, without any software component, without any tape as hypothesized by Alan Turing. But with all the information we have acquired so far, we are now able to understand the functioning of the Turing machine. That is, we are able to understand the logic of the software. So as a first step, let's try to write our first program. Even if we are not technicians, we now have all the necessary knowledge to be able to do so, at least in descriptive form. We don't know programming languages, but languages are quite easy to learn. The important thing is to have a clear understanding of what a computer consists of, and we are getting there. Let's try to write a data reordering program, but before I begin, I want to mention an aspect that we will never tire of emphasizing. The goal of this presentation is not to teach computer science, so don't worry if you can't follow everything or if at some point you get lost, or you would like to better clarify some aspects. I just hope you don't get bored. As we have already explained, you do not have to learn or repeat anything that you have followed. It is enough to hear and remember what you have heard, because what you have to stay with are basically concepts you need to understand about the true meaning of computer science. Whatever the theme, you should not forget that everything is always based on transistors, with which so-called logic bits and circuits are created to compare bits with each other. Bits that represent and are treated as numbers. But there will be time to delve deeper into these concepts. For now, let's follow our first software program. Let's try to write our first program. This is the sort program that reorders data according to a defined criterion, and is a very important component, because it allows to organize them efficiently and to access them immediately. The simplest sorting algorithm is the one we will use, the so-called bubble sort, which consists of comparing two elements of the array and swapping them if they are not ordered. There are other algorithms, much more efficient, such as the quicksort and merge sort, which are useful for handling very large amounts of data. In our case, we simplify the problem choosing a series of only 4 elements, long only 1 byte each, and containing an alphabetic character, according to the standard ASCII encoding. The sequence is initially FCDA, and should become ACDF. We know that a program, according to Alan Turing, is like a tape that goes up and down. Our tape will be some bytes in the RAM, in which the machine code instructions will be written, strings of bits that the CPU recognizes as commands to be executed. For easy understanding, our machine is an 8-bit computer with a bus with 8 lanes. The logic is to sequentially compare all the characters to each other to bring up the lowest value. If we start with the first character, which the computer sees as a number, and compare it to all the others, we will get the A in the first position. We will continue with the second and the third one. We need 3 pointers to point and pick up the characters in sequence. We'll call them P1, P2, P3. Pointers are areas of RAM where we will store the positions of the slots to be compared. P1 equals the first character of the comparison, P2 the second character of the comparison. We're going to do a lot of comparing the character pointed to by P1 with the character pointed to by P2. If the character pointed to by P1 is greater than the character pointed to by P2, we reverse the position of the two characters, otherwise we leave them as is and move P2 to the next position until it exceeds the one pointed to by P3. And that's the program. It's written in assembler, even if it is a language that has not been used for a long time, except for very special software needs that require the highest possible computing speed. Today, all computers have reached very important computing speeds. So other languages are used that are less machine logic oriented and more human logic oriented. In today's languages, this program corresponds to a single instruction. You need just to write the single word sort with some parameters to get the same result. We use the assembler language because, having seen the computer from a hardware point of view in the first part of this presentation, the assembler allows us to better understand the programming logic. As usual, don't worry if you can't understand all the logical steps of this software. You just need to get an idea of what is behind a very simple data reordering program. We will follow the program step by step. Let's start with the first statement that sets pointer P1 equal to 123,000, because we assumed that that's the RAM position of the first character of our characters. P3 points to the position of the last element of the table, that is 123,003. P2 points to the second character, to be compared with the first. CMP statement compares the contents of the byte pointed to by P1 with the contents of the byte pointed to by P2. The computer only knows bits, and thanks to the ASCII standard it can determine that C is less than F, because 67 is less than 70. Then in the next statement the JLE statement jumps if less or equal. In this case it is so it jumps to instruction number 7. P2 points to the next position. CMP compares the value of P2 with the one of P3. If P2 is less than or equal to P3 it jumps to statement 4, and in this case it jumps. CMP compares the content of P1 with the content of P2. P1 contains the character C, and P2 contains character D. Skip to statement 7 if the content of P1 is less than or equal to the content of P2. In this case skip it, and leave everything as it is. P2 points to the next character. Compare P2, which is equal to 123,003 with P3, which has the same value. Skip if P2 is less than or equal to P3. In this case they are the same, so go to statement 4. Compare the content of P1 with that of P2. P1 contains the character C, and P2 contains the character A. Jump if C is less than A, by means if 67 is less than 65. It's false, so we go on to the next instruction. Swap the character A for the C. P2 points to the next character and goes out, beyond the character C. Compare P2 to P3, by means compare 123,004 with 123003. Skip if 123004 is less than 123,003. False, then move on to the next statement. Sum 1 to P1, which now points to the second element of the table, position 123001. Set P2 to the position following P1. P2 points to 123002. Compare P2 with P3. Skip if P2 is less than or equal to P3. Skip if 123002 is less than 123,003. It's true, then jump to the slot 4. Compares the contents of the byte pointed to by P1 with the byte pointed to by P2. Skip if 70 is less than or equal to 68. False, then move on to the next statement. Swap the character F for the character D. P2 points to the next character, the character C. Compare P2 with P3. Compare 123,003 with 123003. Skip if 123003 is less than or equal to 123,003. True, so it jumps in and goes to slot 4. The program continues with the usual logic until the end. With a series of loops that swap the position of the characters, based on the value they have in the ASCII transcoding table, it assumes who comes first and who comes next. The loops end when pointer P1 points to the last position, the one identified by pointer 3, and the program closes. What to remember about this example of assembler programming? As we have already said, this is the first language, no longer used nowadays except for very special needs. Because it is machine-oriented, it forces the programmers to give commands, the instructions to be executed, directly as the machine executes them, and therefore it forces you to reason as the logical circuits of the machine reason. The languages currently used are human-oriented, by means that the instructions are closer to our way to reason and therefore easier to be used. All programs written with today's languages are necessarily translated, or transformed into machine language. In the logic of circuits that deal with bits, only bits. It is technically said that they are compiled, or that they are interpreted. These are two systems by which programs can be transformed into machine language. The only set of instructions that a computer knows and is able to execute directly. The compilation, or interpretation of a language is an extra processing that the computer does for us, to translate written programs in human-oriented languages into machine language. Thanks to the speed of computers, this extra processing does not weigh, and does not lead to a delay in the overall activity, but rather allows the use of appropriate languages according to the different kind of applications. Typically, a single statement in a current language develops into several, or few 100,000 machine statements. In fact, in a computer environment, to display a number on the monitor, as we did on the display of the electronic calculator, involves many elementary activities. Let's suppose you need to display a numeric value, as in the case of the calculator. On the computer, the binary result will first be transformed into a series of characters corresponding to the numeric symbols to be displayed, then transcoding from binary value to numeric characters, according to the ASCII table. You'll probably also want to edit the number. Then the characters must be sent to the monitor once the font, the size, the color have been set. At this point, the number must be transformed into many pixels on the monitor to be turned on, once the exact position where it should appear has also been set. It is evident that compared to the electronic calculator, where it was enough to copy the binary result in the area associated with the display to see the result, thanks to the electronic circuits built ad hoc to do exactly this work. On the computer's monitor, where the result can be displayed in various graphic forms, in various ways and positions, font, dimensions and so on. All this is achieved by executing a series of elementary instructions step by step. It is thanks to the operating logic of the Turing machine. Thanks to the software, many basic generic instructions produce any expected result. The Turing machine, with its tape or software, can do anything, is programmable and therefore extremely flexible. On the other hand, it is clear that every little choice involves a very large amount of machine instructions. Hence the birth of the various languages that make life easier for programmers, thanks to the ability to call very complex functions with a single commands. The difference between different languages lies in the presence of sets of commands geared more towards this or that type of processing. The weather forecast. This time, we will not dwell on the coding of a program. We have seen it abundantly in the previous example of the sort program, and it would take too much time, and we would go completely beyond the objectives of this presentation. What we need to understand from this second programming exercise is not the software language, which we will not see at all, but the problems that are encountered when you have to develop an application from scratch. In this case, let's assume that we want to create a system capable of making weather forecasts. This is an extremely complex subject, but to make the subject easier, we will assume that weather forecasting systems do not exist, and we are called to develop our own that must operate on a very limited territory. A valley in the mountains, inhabited by a small community of mountain people. What's more, the prediction that our system has to provide is extremely simple. It simply has to predict whether rain is expected tomorrow in that specific valley or not. Obviously, this is a simplified exercise as much as possible, just to give you the opportunity to experiment with your current knowledge of computers and programming, how to proceed to create such a system. Which are the general difficulties to be faced and how to solve them. We're computer analysts and not meteorologists, so we start by analyzing the problem by interviewing the locals, to get information on how they usually predict rain. We interview older people who obviously have more experience, and we prefer farmers, who are the most interested in rain and therefore the most attentive to how to predict it. From the interviews, we get a lot of useful information such as: in autumn, when a strong wind blows between those two peaks that are located in the northwest, surely the next day the rain comes. Again, to simplify the terms of the problem as much as possible, we assume that this is enough for us to build the program. We will limit our program to this one and only elaboration. But let's see how you turn this sentence into a set of machine instructions. As computer technicians, our task is to translate the previous statement into bits and program logic. That is, in autumn, when a strong wind blows between those two peaks that are located in the northwest, rain surely arrives. Let's start. We equip ourselves with sensors that can measure the intensity of the wind and its direction, and place them in the appropriate places. These are digital sensors that transform the intensity of the wind and its direction into binary numbers. The sensors can be connected to the central computer, and each of them exposes 2 bytes, one for each value they measure. One value for wind strength and one for wind direction. The computer software will have to read and transfer the data taken from the various sensors connected to it into its RAM memory as many times as it wants. Of course, the computer also has a digital clock that gives it the date and time of the detection, and therefore it stores data in the RAM in this form: sensor identifier, date, time, intensity, and direction. The software we develop will request the 2 values every 30 seconds. It will store them in the RAM, and when it has reached 60 measurements, that is every 15 minutes, it will average all the values and obtain 2 average results. Direction and intensity. If the direction is between a preset range and the intensity exceeds a preset value, it signals rain. At least that's our first approach. At the beginning, the program needs to be calibrated. What is the correct value beyond which there is rain? And after several checks, the software starts to give some acceptable results, even if it often doesn't predict correctly and it is wrong. Then the logic of the program is reviewed. The problem is well known. The computer thinks in terms of bits, that is, something is either true or false. While in reality, this is not really the case. If the average wind intensity exceeds a certain predetermined value, there is not necessarily rain, because reality is governed by much more complex processes, and wind intensity alone is not enough to predict the rain. The phenomenon of rain is much more complex. We should be able to measure many other factors. But for didactic purposes only, we have assumed that in our case it is not possible to measure anything other than the intensity of the wind, to show you how in these cases the processing capabilities of the computer are exploited to map reality, when it is not possible to have all the phenomena under control. Mathematics, statistics, analysis of the distribution of data, fluctuations are used to recognize whether through the analysis of numbers it is possible to empirically identify series of numerical values that can serve as an indicator in identifying the occurrence of complex phenomena, in our case the rain recognizable through the intensity of the wind alone. And so, in our example, it is decided to develop a new version of software that does not limit itself to analyzing the exceeding of the threshold, without contextualizing the results within a scenario of historical data collected over time. The distribution of values and their frequency are mathematically analyzed and better results are obtained. In other words, the reference threshold assumes different values depending on the statistical mathematical processing carried out on the values of the past. Thanks to the systematic and well-organized historicization of the data collected, a reference database is created that undoubtedly provides this new version of the software with useful elements to determine the forecast in a better way. Although it must be said that minimal climatic variations from year to year are enough to distort the forecast from a strictly statistical point of view. The exercise that we wanted to follow on the programming of a weather forecast software with all the constraints and limitations that we wanted to introduce was intended to make you touch with your own hands how the computer, the Turing machine, is nothing more than a calculator that performs mathematical calculations driven by the software, or if you prefer, driven from the famous Alan Turing tape, which goes up and down according to the occurrence of certain results, analyzed according to the logic programmed by a man. Therefore, the quality of the processing results is directly dependent on the mapping that we are able to make of reality using bits, numbers and algorithms encoded in the software. Garbage in, garbage out. In the exercise we have just concluded, we wanted to highlight the difficulty of faithfully mapping reality, having less information available, only the intensity of the wind. Nevertheless, the computer proves to be an extremely useful and irreplaceable machine, because the possible inaccuracy of certain results is countered by an incredible calculation speed, far beyond any human reality, which ends up abundantly compensating for any result, even if inexact. Let us remember this again. The computer only sees bits that it treats as numbers. And the comparison of numbers is only in terms of same, different, greater, lesser. If not properly programmed, the computer is unable to contextualize the results, because it always treats them only as any numerical values. And any number is still different from all the others. To consider a numerical value equivalent to another value, at least one percentage must be specified within which the two results are to be considered equivalent. And the computer will do this additional percentage calculation each time, before determining whether the result should be considered inside or outside a certain category. But it is not a definitive solution, because the percentage is also a numerical value that in turn could be affected by the same problem. It cannot be considered as a fixed constant, but variable according to the context. It seems like a problem without a solution, even if computers are very useful even so. We will see in a moment how the processing of images, sounds, texts has made it possible to enormously expand the amount of software products capable of doing many things in many fields. For example, it is now common to edit a photo, create new images, produce movies, use the computer to translate, dictate, read a text. Over the last few decades, various software products have been created which, with their technologies, have enriched the IT heritage with specialized modules capable of carrying out the most varied processing. If we take as a reference the electronic calculator on the one hand and the use of one of these software products on the other, for example the editing of images, or the reading of texts, or the production of a film, we have an analogy in the use of the instrument, with the calculator. The user types in the data according to their reasoning to calculate the final result. With the software product, the user selects in sequence the elementary functions made available by the product to produce the movie or modify the image according to his needs. In both cases, it is always the user who decides the sequence in the execution of the elementary functions. In the case of the calculator, it adds, multiplies, subtracts, etc. In the case of the software product, it performs basic functions such as erasing an area of the photo, changing colors, optimizing graphics, and so on from the point of view of the machine. In the case of the electronic calculator, we have electronic circuits built ad hoc to perform the individual elementary functions. In the case of the software product, similarly, we have elementary software modules built ad hoc to perform certain basic functions. It is man who decides the sequence and introduces the values. Selects the functions he deems appropriate. It proceeds according to its own reasoning. He has total control of the machine that he processes according to his orders. Over time, some of these elementary functions have become more and more sophisticated, so the electronic calculator has developed more advanced functions such as square root, trigonometry, expressions. And software products have grown to provide increasingly intelligent functions, i.e., capable of autonomously carrying out increasingly complex tasks, relieving the user of this. If we want to stick to the analogy between the all-ardua electronic calculator and software products, we can observe that something was missing that would allow the computer to provide a complete final product, without the direct involvement of the user, who selects step by step the function to be activated. Something that resembled the weather forecasting system that, once fine-tuned, makes forecasts without the user's continuous intervention. We have just seen that there are now an infinite number of software modules capable to perform a wide variety of elementary functions in any application area. Graphics, sounds, speech, text, animation, just to stay in the multimedia field. Why not to build a chain of these modules, specific to a specific type of processing? Let's suppose to specify a sequence of modules, activated by a simple click, able to produce a complex processing that would take us a lot of time. Just for example, let's say we want to create an image of a rural landscape. A green expanse to which we can add some trees, some sheep, a clear sky with a few small clouds, or a cloudy gray sky. It would certainly be a very trivial image. But it's easy to imagine how a software could superimpose the images of the individual elements, like meadow, sky, sheep, trees, and then modify the final result, acting on the colors to depict a sunset, or sunrise, or night with the starry moon. Such a chain of modules could generate an infinite number of similar, but different images, if it were programmed to choose whether or not to put the sheep, decide how many, determine where, and so on for all the elements. We could also choose from a variety of lawns with or without flowers. There are an infinite number of variants that can be predicted by parameterizing the modules of the chain, that is, by inserting variables, which according to their value, condition the choices and make the image generate in a different way. Each time you run the chain and provide a set of parameters, you get a different image, tied to that set of parameters, even though all the images fall into the same category of paintings that represent a rural landscape. Well, before we continue with artificial intelligence, let's now focus our attention on two terms that we will need to know shortly. Concepts and patterns. Let's start with the definition of what concepts are. For the ancient Greek philosophers, the concept indicates the essence, everything that remains stable, constant, beyond the different aspects that our perception, our determined experience, may assume. Example: a dog is conceptually an animal, with 4 legs, the tail, a muzzle, often the tongue sticking out, it has hair, it barks, it wags its tail, it lives at home, it runs on the street. It doesn't matter the race, the size, the color, which are not part of the concept. It could be a big dog, or a small dog, black or white. A child doesn't hesitate to say boar, if he sees a dog regardless of breed. Shape of muzzle and ears, because it responds to the concept of a dog. And he doesn't confuse it with a cat. In front of a particularly large, white dog, he might think that it is a sheep, but only if he is a very young child, because immediately afterwards, the concept of dog will be enriched with new elements that will no longer make him mistake. This ability of the brain consists in experimentally identifying certain characteristics of the dog that serve to identify and distinguish it from other animals. Now let's move on to the meaning of the term pattern in computer science. A pattern is a simplified representation of an object, system, or phenomenon, which allows us to study its properties and predict its behavior. In other words, in computer science, a pattern is a mathematical description of a complex system, which allows us to analyze it and reproduce its behavior through the logic of a program. For example, a mathematical model can be used to simulate the behavior of a physical system, as we saw with the weather forecasting exercise. Although this was a deliberately minimal approach, in our case the pattern consisted of predicting rain by measuring the direction and intensity of the wind between 2 specific peaks. We wanted to dwell on the meaning of these 2 terms. Concept, as far as our brain is concerned, and pattern, as far as computer science is concerned, to anticipate the last topic. Artificial intelligence. Because the last frontier of computer science, artificial intelligence, is the result of the attempt to simulate the processing of concepts by our brain through new computer patterns in data processing. But before we go any further, let's fix the things to remember. Let's summarize the main points we addressed. The transistor, the integrated circuits, the bits, the RAM, the numbers and the binary math, the operation of an electronic calculator. Then we also talked about logic circuits, and or not, Alan Turing's machine, and finally the computer. We have seen the program written in assembler. We talked about the challenges of programming a weather forecasting system. The limits that derive from the rigid logic of the numbers that in the comparison between wind intensity and reference value can only give us rain yes or rain no. While the reality is much more complex than a simple yes or a simple no. We also found an analogy between the hardware architecture of the electronic calculator and its use by the user on the one hand and the use of specialized products of graphics, multimedia, and text management on the other hand. In both cases, it is the user who interacts with the machine and selects step by step the functions he needs to complete the expected result. The case of weather forecasting is different, and also the chain of elementary functions to build a rural image. Both programs do not require interaction with the user, and both programs produce different results depending on the input parameters that condition their processing. The intensity of the wind to establish rain yes or rain no. The set of input parameters to create different images. But note that for the weather software we talked about a program, so we assumed that the software was written by a programmer, who also had to make several versions before achieving an acceptable result, even if, due to the rigidity of numbers, he was never perfectly satisfactory. In the example of software that creates country images, we hypothesized to create chains of pre-existing modules specialized in elementary functions. We chained them according to a pre-established sequence, and we provided a set of parameters to modifying their behavior, until we obtained a set of modules to produce rural images, different according to the input provided parameters. A set of parameters, think of it as a sequence of bits, that always produces the same image. This is the end of the second part. With the third and final part, we will talk about artificial intelligence. Thank you for your attention and have a good day.